Osmosis, is just a special version of diffusion we talked about last time, but instead of looking at some solute moving, we're actually thinking about the solute being constrained by some semi-permeable membrane and the water moving instead. It's worth talking about some terminology that we use a lot about osmosis. Let me just do that briefly here. Let's start with a blood cell. What is the osmolarity of just what all of the dissolved stuff inside a blood cell?
0.3.
Exactly, 0.3. You know that this is going to be at 0.3 osmolar, because that's basically almost everything in the body is at 0.3 osmolar. So let's think about putting this blood cell in different kinds of solutions. I'm going to have 3 cases. I'm going to have one where I'm putting it into distilled water, one where I'm going to be putting it into like 0.3 osmolar, and one I'm going to put it into something that's 0.6 osmolar. So these are different solutions of whatever. This is, well, this is just water, so it's not a dag nabbit. There's my water. This has something dissolved in it, who knows what. It could be salt or sugar or whatever. If it was salt, what is the molarity of the salt that would give me 0.3 osmolar?
Would it be 0.15?
Exactly.
Mm.
Right? If I had 0.15 molar NaCl, because each Na and Cl becomes independent, we just double that. So that becomes 0.3 osmolar. Right? So 0.15 molar NaCl is the same as 0.3 osmolar. If it was glucose, just sugar water, what would be the molarity of the glucose to give me that osmolarity?
0.3.
Just be 0.3. They're the same. Exactly. What would happen if I had 0.3 molar NaCl? What would it become in terms of osmolarity?
0.6.
Yeah, exactly. 0.6. This could very well just be 0.3 molar NaCl, right? 0.3 molar NaCl dissociates into 0.6 osmolar because every NaCl becomes 2 independent particles. So that all makes sense? All right, so now let's take our blood cell and put it in these different things. So in this first case, again, we always start with like what is in the cell itself, and we know that within the cell is 0.3 osmolar. What is the osmolarity of distilled water? How many particles per liter do we have in total in pure distilled water?
0.
Zero. Right? There's nothing. There's no distilled water means there's nothing dissolved in there. So I have 0 outside and I have 0.3 inside. So whenever you have a solution that has a lower osmolarity than a cell, you say it's a hypoosmotic solution. So hypo meaning below, right? Hypodermic needle goes below your skin. Hypoosmotic. If I have, again, 0.3 inside, 0.3 outside, if it's exactly the same inside and outside, I call this an isoosmotic. Iso means the same. right? Isometric exercises where you don't change the length of your muscles. Iso just means same. In this case, where it's more than inside the cell, it's a hyperosmotic solution. Hyper, right? Whoa, you know, it's more. So hypoosmotic, isoosmotic, and hyperosmotic. This just has to do with comparing the osmolarity inside to outside. And the inside is always 0.3. So basically, if the solution is less than 0.3, we call it hypoosmotic. If it's exactly 0.3, it's isoosmotic. If it's greater than 0.3, it's hyperosmotic. And I should say, just for completeness, this 0.3 is somewhere between like 0.28 to 0.3. But let's just say 0.3 because it's easy. So that's one thing we care about. The other thing we care about is what happens to the cell. You know, is the cell, what's going to happen with osmosis? And so there's this other term, tonicity, that you need to know. Tonicity is kind of like the pressure. Which way does the water go? And in this case,
11 a.m.
In this case, you have to kind of remember tonicity is water moving rather, and it's going to be related to osmolarity, but it also is related to some other things as well that we're going to see in a few moments. So back to this picture, we are going to assume, let's assume non-penetrating solutes. So assume whatever is making the osmolarity inside and the osmolarity outside cannot cross the membrane, and they're locked on either inside or outside of the cell. This is not always a good assumption. We're going to, in fact, our lab next week, we're going to be working with some penetrating solutes like glycerol and urea. But for right now, let's assume, what's an example of a non-penetrating solute, something that can't cross the membrane without help?
Ions?
Say it again.
Ions?
Exactly, ions. Sodium chloride is a non-penetrating solute. What's another non-penetrating solute? Glucose, a big polar molecule. So if we're talking about those kind of things that can't cross the membrane, then that's the situation we're in. So now let's think about tonicity, which way the water is going to move. If I'm in a hypoosmotic solution, less osmolarity outside compared to inside, which way does the water move?
Into the cell.
Yeah, the
Out of
water's
the
going to
cell?
move in. The water, remember I talked about kind of the salt draws the water in. So this is going to be the water moves in. This is called hypotonic. Water moves into cell. So depending on how strongly hypotonic solution it is, it might just kind of swell. If it's strongly hypotonic, it might be enough to pop. If the cell pops, we call that hemolysis. Lyse means to cut open. So hemolysis, cells break up. If it's really strong, that happens if you put your blood cells in distilled water, they all explode. they just spill their hemoglobin into the solution, and it just becomes this big red solution of free hemoglobin. There's no more cells in there anymore. All the cells have popped. What about if I have an isoosmotic solution where it's balanced inside and outside? What's the net movement of water?
0.
0.
Isn't it gonna go? Oh, I thought it would go both ways.
Right, but there's no net movement of water. So water can cross, so water can move out and it can move in, but there's just as much of a tendency for water to drift out as drift in, because there's no difference in the osmolarity. So this is what we're going to call isotonic. Now I'll say no net movement of water. Because no, you're right, the water can come in and out, but ultimately you're not going to have more coming in versus coming out. So it's not going to inflate or deflate ultimately. You
I have
know,
a quick question.
uh-huh.
So when you're using terms like hypotonic and isotonic, is it only relating directly to water, or is it just any type of movement of fluids through the
It's-
membrane?
No, it's the movement of water in or out of the cell.
I have a question.
Uh-huh.
So this would not be oscillating back and forth, right?
I mean, when I think of oscillating, I think of a more regular kind of bouncing. This is more just, random. It's like there's some party going on and sometimes people are coming in, sometimes people are leaving, and on average, you have the same number of people leaving per hour as are arriving at the party per hour. So the party isn't actually getting bigger or getting smaller. The people who are actually at the party are kind of changing, but it's not like some thing where someone's going in and out and in and out and in and out and in. That's when I think of oscillating, when there's some actual kind of bouncing going on or something. So it's more like or I don't know, a party, museum, the museum. Across the course of the day, people are entering the museum, people are leaving the museum. On average, there's always about the same number of people in the museum, but there's no net movement in or out. But that doesn't mean there aren't people entering and leaving. But overall, the balance is the number of people in the museum isn't changing. Same thing, the water, some water moves in, some water moves out. But as you just look at it over time, it's not inflating or deflating. So I put a happy face here. This is why we came up with our IV flush syringe to be 0.3 osmolar. It's isoosmotic and isotonic. And that means that when you shoot it up into somebody's vein, that the blood cells are going to have a little smile on their face, because it's like, this is just what we like. So what about if you put this poor blood cell into this 0.6 osmolar?
It's gonna shrivel up.
Yeah, the water's going to leave. The water goes to where it's more salty. We're going to get what we call crenation, which it gets all kind of shriveled up. And we call this a hypertonic solution. So H2O leaves the cell. So this is like, over the weekend, spend some time with these terms: isotonic, hypertonic, hypotonic. Again, that has to do with the movement of water. It's related to these hyperosmotic, isoosmotic, hypoosmotic. But as we're going to see, there can be things that make the relationship more complicated than what you see here. If it's a non-penetrating solute, then the relationship's super easy. It's hypoosmotic is hypertonic. I mean, hypoosmotic is hypotonic. Isoosmotic is isotonic. Hyperosmotic is hypertonic, assuming that the solute does not have the ability to cross the membrane. I'll show you the reason why it's not always true though. Like assume a penetrating solute. Like for example, urea. Urea is small enough that it can cross the cell membrane without any help. So I'm going to take 0.3 osmolar urea. So this is isoosmotic urea solution. You know, I'll make the ureas little yellow things. Maybe I'll make them. Right, urea is a little nitrogenous thing. That's from the breakdown of amino acids and stuff. So we have, 0.3 moles of urea per liter. It's just a concentration of urea molecules floating around in there. I'm going to put my blood cell in there, which is also 0.3 osmolar. So here I have an isoosmotic solution, but it's a penetrating solute. So the moment this hits the solution, maybe for a fraction of an instant, maybe things are okay, but after the first instant, things are not going to be okay anymore. Because there is not urea inside a cell normally. Normally, urea is not inside a cell. It's a waste product that you get rid of. So how much urea is in the cell to start with?
None.
None. There's no urea. But there's a whole bunch of urea outside. So I have a whole bunch of urea outside, no urea inside. Which direction does the urea want to go if we just look at the diffusion gradient of urea?
Into the cell.
No.
It wants to go into the cell, high to low. It's 0.3 out here, 0 in the cell. So urea wants to come in, as did the glucose or the sodium chloride, but they couldn't because they couldn't cross the membrane. What happens though with urea, because it's penetrating, it wants to come in, and by Jove, it can. So the urea crosses the membrane and the urea starts coming into the cell. What's going to happen to the osmolarity inside that cell as I start adding more solute in addition to what's already in there?
Gonna go up.
It's going to go up. Starts going up. And so now all of a sudden I have a higher osmolarity in here. So maybe this is going up to 4 or 5, whatever. It's still 0.3 out here. What's water going to do now as the osmolarity in the cell starts going up?
It'll want to go in, right? Or
It's
out?
going
In?
to want to go in, right? It goes to where it's more salty. So urea enters, the water follows. Because as the osmolarity is increasing in the cell, the water is going to come in by osmosis and kind of dilute it. What's going to happen to the cell now?
Hemolyze.
It's going to start blowing. It's going to start inflating and probably hemolyze. So so this is an isoosmotic solution. What is it in terms of tonicity? If water enters the cell, what do we call that?
Hypotonic.
Atomic.
Yeah, exactly. So remember, hypotonic if water enters the cell. So here we get this kind of fascinating thing. This is hypotonic. I should do a larger. It's hypotonic even though it's isoosmotic. right? So that's where you have to be careful. In our lab next week, this becomes important because we have a couple of penetrating solutes we're going to be working with. So this idea of a solution, and again, obviously it makes sense to understand the details of what can you put in somebody's body and not explode their cells, right? This is all about what kind of a solution or how a particular solution is going to affect your body cells. You have to think about two things. You know, if I have a red blood cell and I have it in some solution, and I want to know what's going to happen to this puppy, what are the two things I have to think about?
Osmolarity.
I have to think about osmolarity. You know, is it greater than 0.3? Is it equal to 0.3? Is it less than 0.3? That's going to make a big difference. And what's the other piece of information I need to make a definitive prediction?
The
If it-
tonicity.
How do we figure that out?
If it's penetrating or not?
Yeah, is it penetrating or not? So these are two things that you are going to need to pay attention to when you are trying to predict how a cell is going to react in some solution. And then you have the information you need, the stuff we've just been talking about. If it's non-penetrating, then it's easy. If it's less there, then if it's less, then it's going to be hypotonic. Water is going to come in. If it's equal, it's isotonic. If it's greater than 0.3, it's going to be hypertonic. Water is going to leave the cell, it'll shrivel. If it's penetrating, then you got to be careful because it can even be isoosmotic, but still be hypotonic because the penetrating solute enters the cell and then the water follows, which ultimately ends up inflating and bursting the cell. So does that make sense? So in fact, I can just, I'm going to share. Modules. So this is something you just have to do before next Tuesday. You got all weekend and the beginning of next week to do. This fluid balance and RBCs lab. You know, first there's the Prelab. There's a little thing that I made that basically talks about what I just talked about. To review it again, I gave you a little PDF thing, which it'll be, you know, don't actually print this out and type it in. You know, you can make this chart yourself in your lab book, but basically we're going to have different kinds of solutions and you have to predict what's going to happen to the blood cells when they go into these different solutions. So this PDF here is just to try to hold your hand as you start thinking about this. You know, does it dissociate? You know, if it does, into how many particles? Therefore, what is the osmolarity of the solution? Like you've got the molarity, but you want to know what is the osmolarity that's going to relate to the dissociation. And then, you know, compare, is it hypoosmotic, isoosmotic, hyperosmotic? It's just going to be comparing it to 0.3, right? So this is just what I've been talking about. Then you got to think, is it penetrating or non-penetrating? Just as a spoiler alert, salt and sugar do not penetrate. You know that already. Urea, I just kind of told you it does penetrate. Glycerol. Glycerol is like an alcohol, which does have it has hydrophobic and hydrophilic properties. So glycerol typically does have an ability to get into hydrophobic domains. I'm going to leave the ammonium chloride as let you figure that out. That one is kind of, it's an interesting thing. I'll talk more about it after we do things. But your prediction, what do you think is going to happen? Is the cell going to swell or hemolyze, no change, or is it going to shrivel and crenate? So this, as you come up with your hypotheses, it's going to just be what I've talked about. You're going to have to think about the osmolarity of the solution and how it compares to 0.3. Also worry about if it's penetrating or non-penetrating and make a prediction. It shouldn't be that tricky once the concepts are clear. But this is going to kind of force you to really think about the concepts to get them clear. Why, yes, Ms. Woods.
But it doesn't make a difference if something is regularly occurring in a cell versus not. Like with urea, we looked at it. Urea, you said, isn't naturally occurring in a cell because it's a waste product, and therefore it's going to rush in. But isn't there an equilibrium if there's already some in the cell?
So what I would say is that 0.3 is resulting from lots of different things. So any particular individual thing that you're thinking about is going to be much less than 0.3 because it's just one little piece that contributes to that 0.3 moles of total particles.
Okay.
So yeah, any individual thing you think of is going to be way less.
Thank you.
So I just talked a whole
I have
bunch.
a question real fast. How do you determine if something is penetrating or not penetrating?
So you tell me, what were the qualities of things that could penetrate a cell membrane without help?
It's non-polar, it doesn't need help.
So non-polar.
Small.
And if it's polar, then it's super small, right? So again, that's what I was just talking about urea. Urea is polar, but it's dinky. And it does have an ability to kind of jam through the membrane sometimes. Glycerol, I said, is an alcohol.
Where that document was that you just showed us?
What's that?
Where is that? I can't find where that document you just showed us was, that chart.
Let me make sure that it's shared properly. So if you go to lab, fluid balance and RBC pre-lab, and it should be visible. And then intro to fluid balance and RBC lab and pre-lab guidance. So that should be there. And if you click on that, it should have the stuff that I just showed you.
I see it, thank you.
Later today, I will activate the submit PDF of fluid balance and RBC pre-lab, which is just going to be your objective and hypothesis. Right, in your objective for this lab, what are, just from what I've been saying, given that we are blah, 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 blah. Hold on, where's my, oh, I didn't. Now I want to go back to this table. You can see what kind of things are we changing the independent variable in the different solutions.
Similarity.
One is we're changing concentration. Exactly. We have different concentrations of our solutes. And what's the other thing that is changing?
Penetrating and non-penetrating.
Yeah, just kind of the types of solutes themselves. So we kind of have two two independent variables. One is differing kinds of solutes, and then among those solutes, different concentrations. Right, and then our dependent variable is ultimately going to be what?
The solution,
No, the solution is,
Osmolarity.
no, that's going to be part of our calculations to figure out, but we're kind of,
Tonicity.
The type of the red blood cell.
what's that?
What happens to the red blood cell?
What happens?
Mm.
A dependent variable is going to be like the fate of the red blood cell. Does it explode? Is it happy? Does it shrivel? Right? So that's our dependent variable. That's the thing that we are going to make predictions about in the hypothesis and then actually check for when we do the actual experiment.